Good morning, Peter.
Hi, Alan.
How you doing, sir?
Doing well, and you?
Good. Running a bit late, so apologies.
Hmm.
Although I'm on time, but normally I'm a bit more prepared.
So your meeting went well?
Yeah, I did. I got my own recording of the presentation, but OCP normally launches them all, so I tend to wait for that one to go out. I'll let everybody know. I'll populate on LinkedIn and input a link to all the members of the group when it comes up.
Yeah, if you're willing to share your slides, I'd be interested in that too.
No, absolutely. Well, in fact, the final ones, I think they're already on the wiki, but the final ones are a couple of typos changed. But yeah, I'll forward them to you.
Thank you.
Yeah. In fact, just let me open that now, just while we're waiting, see if anyone else wants to join us. Okay. All right. Give it a couple of minutes. Yeah, so what I did do, I don't know if you know Rolf Brink. He sort of is one of the guys that drives all of the cooling efforts within OCP.
Okay.
And, so he's big into the immersion. I mean, that's his speciality. But he had a dinner on the first night so I went along to that and met a bunch of thermal people, including a lady actually that specializes in the chemicals. She's from the chemical industry, so she specializes in the cooling stuff.
Yeah.
I had some good conversations with, and I watched a two-phased presentation, which I'll give you a link to as well, which was a guy that's doing two-phase stuff and talking about the capabilities with two-phase, talking to your point of the efficiency of the thermal transfer compared to the liquid. And so I managed to corner him and got him. He came to the presentation and he did give me his card. I do need to follow up with these people. So I mean, in theory, we're in that area. So I managed to get a good few people to come along. One of my main guys is a guy called John Summers from the Research Institute of Sweden. He's another Brit actually, and he was always asking lots of questions about using water at last year's regional summit, and so he came along, and I guess the biggest point that was raised with those guys of concern was when your liquid boils, you get this cavitation where you end up with a bit of the silicon area, the hot spot being dry because it boils, right? And it leaves there. And so you've got to be careful not to go into a vicious boiling mode. It's got to be in that transfer zone. So it boils, but it doesn't boil it dry.
Yeah. Because a bubble is an air bubble and not a water bubble.
Exactly.
Yeah.
And then you've got to control that extremely carefully.
Yeah.
And so that was the biggest thing. But in the conversation, obviously, if we're pulling the vacuum, as soon as you start to boil, the vacuum drops off because the pressure rises, right? And so it's a natural control. So as it boils, the water is going to have to boil at a hotter temperature because the pressure drops.
Okay.
You follow me? That makes sense.
Let's see. So why does the pressure drop?
Well, because when you start boiling, you expand, and therefore your 0.2 bar that you're pulling and not boiling, as soon as it starts to boil, the liquid and the gas fills more space, so the vacuum reduces.
Yes,
Is that
the
right?
pressure increases, right? The vacuum reduces, and the boiling point goes up.
Will rise.
Yeah,
So
that's right.
we'll naturally stop ourselves from boiling too crazy, because as soon as we start to boil, we'll stop boiling.
Yeah. Mm-hmm.
And as soon as we stop boiling, the pressure will build again.
Yeah.
So if we get it, so now, and also the liquid ring vacuum pump it's going to be a slow, from a control loop perspective, it's going to be a slow control loop. You know, if we needed to turn the speed up because the vacuum's dropping, so we would see the vacuum drop. We might actually begin to increase the speed, but it'll be a slow time constant compared to the certainly the speed of the processor.
Yeah.
Now, this other thing this lady, so I think this lady might have said about this on the chemical side. And the other thing this lady said, well, she was saying, I think it was her that might have brought it up with me first. This is why I love talking to the experts. It's fantastic. They all tell you why it won't work. And then you go, okay, well, okay, how do we get around that problem?
Right.
So what I realized was as well is, and I've realized this for a while now, is the time constants of all of this thing. If we're trying to control the water for 65 degrees C out,
Right.
and so we got a valve on the flow of water into the module to keep the temperature coming out around 65 C. That's a very slow control loop. You know, moving mechanical valves are slow control loops.
Right.
The motor is a slow control loop. And so everything inside this system is a complex, you know, it's still a control loop, but it's a slow time constant. Whereas the GPU, if you go from doing nothing to doing a full-blown workload, you've got nanoseconds worth of going from no heat generation to massive heat generation, to
That's
massive
right. Yes.
And so therefore, I mean, what we do is we get into this stable position if we're pulling a 0.2 bar vacuum, but instantly the GPU goes up to temperature, and we're going to need to open the valve up to make more water flow, and it's going to be too long a time constant.
Yeah.
And then what I realized is, if we're in control of the GPU as well, all you do, they already have turbo mode, so you just throttle the clock down. So if you say, oh, you're bringing on a big load and suddenly you've whacked the power up, you say ramp back the clock until the cooling system catches up. Now, the lady's argument, which she's got a very good argument, is my customers will not allow me to slow down the compute for my thermal design. And I said, well, yes, technically, but they do, you know, they do at the end of the day, if you're running a big job, this running for minutes or hours, we're talking milliseconds or maybe a few seconds for the control loop of the pumps to work.
Right.
So you're only talking, so yes, whilst that's a problem, you suddenly go from one load demand to another load demand. And you have to and you have to say, well, hang on, Mr. GPU, you have to wait a second. We can't give you it right away. Assuming the job's running for minutes or hours, that's still a very small percentage. So it might be an okay thing to sacrifice.
Yeah.
Anyway, that's where my head was going. And I don't know, maybe, yeah, I'm not too sure. But it's a complex problem, and it needs participation from all the players.
Did anyone talk about the difficulty of pumping a mix of water and gas?
No. I talked about a liquid ring vacuum pump. Nobody jumped on me on that. I think I did raise it with John Summers, but I don't think anyone was really close enough to that.
Okay.
Because I said a liquid ring vacuum pump. I said I asked ChatGPT and it said, hey, it should work if you've got some gas. So I guess where my head was at with that was, I mean, that's another experiment, right? Or another liquid ring vacuum pump expert you'd have to talk to. Like if we had 80% liquid or 90% liquid.
Yeah.
So you had air under a static situation, you would have air at the top, and then the liquid ring vacuum pump would start pumping in.
Yeah.
Maybe you need to prime the liquid ring vacuum pump. You need to pull a little bit of water in from somewhere else to prime it to get it to seal. And then it starts pulling the stuff through and it starts mixing the water and the air. And is that good enough to make it pull the vacuum? I mean, that's obviously a big unknown. So I think that's where we need to maybe phone one of the. Now, the other big thing that I think is missing from my analysis is I've got these columns of modules, right, where we got 8 of them, so we're in the region of 15 kilowatts, sort of region. So we need to pull a vacuum, and we've got this flow. Oh, by the way, the guy that was talking about the gas, 2-phase versus 1-phase. In his presentation, he said, the beauty of 2-phase is also you don't need the flow rate. You can go with much smaller pipes because you don't need the flow rate for the same amount of cooling.
Yeah.
And that's, I think, if you look at the Blackwell machine from NVIDIA, that's got huge pipes going in and out of that stuff, but that's single phase.
Yeah.
So maybe our 11 times difference in thermal transfer will give us that ability with our small pipes. But the question is how big does a liquid ring vacuum pump need to be to pull 0.2 bar on a certain small, very small flow rate? I think that's another question we need to ask ourselves.
Yeah.
So, I mean, for me, it looks like a real fun experiment if we had some money to do it.
Yeah.
However, we don't have any money. So, so I'll bring the slides up, and what I'll do is I'll repost the slides actually, and I'll give you a link to the post on the wiki.
That's great.
Let me just bring up the slide again so you've got it. If you should almost think of it from memory. Okay, can you see that?
Yeah.
So this was the slide. Let me make it a bit big. Let me put it in play mode. There you go. Can you see that? So that was what I went through. That was what I changed your reference to. So as we agreed.
Yeah.
So they're there.
Yeah.
But that specialist that did the presentation on 2-phase did come up to me afterwards and said, be happy to have a chat.
Yeah. Well, I apologize, Alan, but I have to skip. I have to go to another meeting.
Oh, yes, you said.
Yeah. So I appreciate the update, and I look forward to seeing the slides.
Yeah, okay. I'll just record this and I'll put it on the wiki, and I'll ping you to let you know. Or you'll see the HPCM messages, won't you?
Right.
All right. Okay, Peter.
Take
Thanks for
care.
coming on for a short time. No problem.
Yeah.
Cheers.